My name is Artem Chumachenko. I'm an assistant professor at the Science Studies Laboratory here at Warsaw University. And today I will be presenting an ongoing research on complex analysis of complex networks. It's also a complex analysis of knowledge network. And I will in detail explain what we mean by thermodynamic framework for this complex network. And we will be studying the data collected from scientific publications, in particular field of science, but the size of this sample will be, I think, enough to say that we will try to capture some general properties of knowledge networks in general. And I would also like to mention that the main goal of today's seminar is not only to present some results that we have, but encourage to study these concepts, knowledge network, because they exhibit a lot of interesting properties, and I think would be very beneficial in terms of other disciplines, which methods can be used here in this analysis and promote this network, this setup, because it provides a lot of experimental data that usually are not present when we study complex networks. Not always, but at some points we have a lot of theory, and to test the theory we need an experiment. In most of the cases we try to go to the physical systems which require complicated setup and well, preparation to get the data for analysis. In this case we have a system which can be studied in dynamics almost at atomic level. So we know and record all the data that goes to the system with great precision. And how deep we will go to this precision depends, of course, on our computational power that will enable us to go deeper. But we kind of have in slow motion the recording of the dynamics of a complex system, which can be analyzed and gives real feedback about its properties, and in this way test the theories that we have available for analysis of these particular networks and many others in biology, in environmental sciences, quantum physics, and many others. Well, I would like to start with the more concrete things. From the phrase that the history of humankind can be summarized in a series of keywords. I recently found this paper that this is the first words of this paper, and I think it's very precise in terms of explaining why we studying this network and why the the concepts that we are studying, the keywords, are essentially important in terms of knowledge. I would also, well, reformulate maybe this in terms that the physical concepts, the history of science, can be represented as a series of physical concepts and their evolution in time. And the evolution in time is really depends on the context. And this context is changing, and we will try to quantify this context via this well, knowledge network that we have. Why we studying this? Well, we know that scientific documents remain the main source of scientific information exchange. It's historical fact that almost all the information we get from the literature, and extraction of information from the literature is made by humans. And because it's rather complex knowledge to extract, to process, and bring some novelty. But in our days, we have a problem that, well, the publication rate is accelerating. The amount of information that we have from scientific publication is increasing every day. And for this, we need to have some new tools that will help us to work with such amount of data and extract some valuable information, valuable knowledge out of this. We can present scientific knowledge in terms of concepts, as was already said, that, for example, the evolution of a meaning, for example, word of energy through the years of scientific study, scientific evolution was changing. It keeps its core meaning, but in context, it's always changing. And if we say about, for example, electricity, we mean by energy something precise, mathematically precise. But when we said about energy in terms of information science, it's something which is in many cases, well, not justified or misunderstood, because we say, okay, information is energy, and we can find this statement in many research papers, but to quantify this, it needs to have a model, and I hope we will present this model today. The useful idea that we will present today also, a few slides later, it says that how, for example, meaning of a concept is changing. The meaning of a concept is changing due to some useful information that we have somewhere in the literature from where we take this knowledge. This useful information should be quantified somehow. It can be assumed that useful information is something like useful work in thermodynamics that has to be somehow increased if we want the scientific production be more effective. And we will try to bring this analogy here and try to quantify how we can bring this concept of work from thermodynamics in terms of information science and this knowledge network that we are studying. Of course, these changes of meaning can be presented like a cultural holes between different disciplines or different subjects that are studied. And these cultural holes is also, well, it has a lot of explanation and a lot of research devoted to these cultural holes in terms of philosophy, in terms of how we can build a computational theory of discovery, for example, by bridging these cultural holes and introducing these novelties. But most of the time we have more empirical discussion, that it's needed to be presented in order if you want to have a novelty in the system. So it leads to, we need more collaboration between scientists, and we need to pay attention to some multidisciplinary projects that will bring together different disciplines and bring something new. But the main question, how we can quantify this, what we can do about it. And well, I said before about the problems that now we have many more information that we can analyze. This is good from one point of view and bad from another point of view, because it's too many, but good that we have some tools to do that. And well, these tools already exist, at some point, and many of us know these tools like connected papers, ProfiScience, leap maps, undermined ACE maps, or very famous now ChatGPT. It's all tools that are used to dig through the information and present it in a form that would make life for the researchers easier. But all of them mostly, well, they have a different background, I would say. They originated from different methods of data analysis, but in most cases they are pretty bad when we discuss the dynamics. All those models that we have, which are behind these tools that presented here, they are trained on some set of the data. It's a huge set, and it has huge amount of parameters to kind of map this multidimensional landscape of the data that is present up to date. But if this is changing, constantly changing with time, we need to build new and train new models. Of course, to build a bridge between old model and new model, it's a problem. There is a method to do that today, but in general, it remains a difficulty. We will propose something else, which maybe help us to deal with dynamics more easily. A few words about our data source, and description that we have. I already told that we have increasing amount of articles published every year, and you can see it on our here on right upper corner. We present here only one discipline. It's articles about high energy physics, which was extracted from archive for a period of 1990 to 2018. And you can see every year number of articles published within this preprint server is increasing. We have a little bit less articles in 2018, but it's because our data set is not complete for this year. But we can say that we have to deal with increasing amount of articles every year. And we extract almost 14,380, to be precise, scientific concepts from amount of these articles that was published in archive. And we can see the dynamics here on the figure below, on right down corner. We can see how these concepts was introduced. So when the preprint server was established and we had huge upload of the data there, we can see that the amount of concepts introduced shortly after 1990s, well, rather big, But then when we go further, we have much less new concepts introduced in the database, and well, not all of them explaining some novelties. It could be some names of experiments and some tools that are using for analysis, etc., etc. But we can see that system is trying to adjust by bringing something new into the network, some new nodes, and in this way try to record new information that is constantly kind of uploaded, I would say, in this network. A few words about why network of concepts. We can see that in this network and the distribution of concept citations is same way as the words in the text. It's essentially a power law dependence. To take into account some lack of data that we don't have enough articles to present the concepts, we can make it differently with some exponential cutoff, which we will explain later, but it all fits to thermodynamic analogy. And we can use the thermodynamic analogy to introduce the thermodynamic potentials to describe the state of the nodes of this network. On many levels of organization, this network resembles the fractal properties. This is because of the power law dependence in most of the case, because it's scale-free behavior. Who knows about the power law systems with power law distributions? It's essentially fractal properties. As I said, the historical data that we have allow for exact, almost atomic level, if say in physics analogy, of a dynamic calculations. And we can test a lot of theories on this data set using this dynamic data with great precision. Some of the problems are NP hard, because if you would try to go very deep and try to incorporate all the data possible, then we will face a problem. We will not be able to process, but we will try to use the thermodynamics in order to say what nodes to include, what nodes not need to be included. Yeah. To encourage people once again to do this, yeah, to work with these complex systems. Why it's interesting? Because thermodynamics in physics can be viewed as a special case of information theory. And in this case, to study the systems, we have only information theory. We have some analogy to thermodynamics, but we don't have a space. We have to work in pure information theory quantities like entropy, mutual entropy, etc., etc. And if we succeed here, we can improve the thermodynamics also to understand maybe why second law of thermodynamics is so well powerful. It's not proved from ab initio property, microscopical properties of the systems. We only know it works. Yeah, it works also here, but here we have a chance to understand how it works, why it works, and in this way bring something new to thermodynamics. In this case, when we study this knowledge of these concepts and this knowledge network, we can try to understand how information can be transferred to knowledge. What is knowledge, and how we can quantify the knowledge, and how we can possibly increase the efficiency of a knowledge mining, let's say, yeah, to get closer. And many fields, as I said, would benefit from this. Computational theory discovery is one thing. Yeah, they all try to understand how the novelty can be produced somewhere in the literature. Machine learning. In this case, we have possibility to improve the loss functions that is used in machine learning. And there's already some research how we can use mutual information and understand how the deep neural network should be organized to increase the learning rate, and how we can build this loss function more effectively to reduce the learning time. In quantum information theory, we have a problems of entropy production. And it's kind of can be beneficial. We can infer some methods within this knowledge network how to go to quantum limit. It's not obvious, but it's possible. In neuroscience, we also have networks, and we all have a stochastic information input in many channels, and complex systems are evolving during the time according to this information. We have the same thing here. Testing these methods on this network can benefit also neuroscience models. For the second law of thermodynamics already was mentioning, but for example, Landauer's principle, which is in stochastic thermodynamics or classical information theory, is a very interesting principle. It can be tested with some real data to understand how it works. Maxwell demos. This is very famous concept which is debated through the years, but it would be very interesting if we would be able to introduce some artificial data to see whether can we build a Maxwell demo in this system, and how it can work, to produce for us, for example, useful information. Self-organized criticality systems. This is that what I would mention many more times along other slides, because the systems with the self-organized criticality is also debated very heavily in the literature. But in this case, in this system, it seems to obey this organized criticality because of some properties that I will explain a bit later. And to test this model and to understand how a system goes to the state which is close to this criticality, it's the essential essence of this computational theory discovery. In a sense of this network, if we would be able to understand how we get closer to the state which is about to produce some novelty, we would be able to answer how this novelty can be artificially prepared. which refers for us for maximum them of the game. And well, we will try to quantify information in terms of dynamic complexity. This is a concept that we are introducing here, and I will explain in on the graphs what is dynamic complexity and how it can be viewed in this network. But dynamic complexity seems to be a way to describe how a system accepts new information, how it stores new information, and how this information to knowledge. Yeah? We are dealing with a complex system, and complexity of the system can be manifested like topics, which originated through the stochastic input in this system. And these topics is a manifestation of this dynamic complexity in the network. And we, well, here again, try to map it to the thermodynamics. Let's go to the concept of dynamic complexity and topics in more detail. In this network, we can build a distance between two nodes of a network, which are represented as a concepts. We have some term frequencies which describe for us each concept, and these term frequencies are extracted from the literature. We know how many times each concept was used in particular article, and we have all the time records for this, and we can build a distance as proportional to mutual information inverse to mutual entropy, yeah, in terms of citations of this concept. This similarity matrix is a common thing when you analyze any network, yeah, and studying this similarity matrix can give us, for example, the landscape of a knowledge which is already present in this network. For example, if you would use the minimum spanning tree algorithm on top of similarity matrix, we would see that originally, when we don't have any interactions, every node on the same distance of a unit, yeah, between each other. When the information starts to inflow in this network, it starts to contract. Some nodes tend to go closer, well, in correspondence to a common amount of documents that join these two concepts. But if you would see this structure for a long time, we would see that some of the concepts are heavily connected. And this representation that we have here, it's a kind of landscape of that useful information. It's a footprint of useful information that we have in the network. This picture was presented to specialists in high energy physics, and they don't have an objection that these, well, the collection of keywords or collection of concepts that kind of was extracted due to some seed concept as neutrino physics here is correct. It describes all the field correctly, but now we have, in addition, some relation between them, and we want to understand how this relation is changing over time. What needs to be made in the system to change, for example, or bring a new link, which would be more powerful than we have here, just to change the structure. And that would represent a new knowledge that went to the system. This knowledge is originated as a topics. On this picture, we have here two different time moments for the same topic of neutrino oscillations. On the left, we have its topic on the beginning, when the neutrino oscillation was introduced as a concept, but there was not many literature which was discussing this subject. And after the time, we have many more new concepts introduced in this topic, and it starts to explain the knowledge in terms of these concepts, and the topic is growing. Topic is growing, and in this way, it's creating for us this picture. each step that we have here, we have something like many hyperspheres, which is circles here in this figure. And when the concept is going through the outer hypersphere to the internal, when we have a distances overall closer than some distance, some cutoff, yeah, we have like evolution of the topic. We have more dense structure in the concept space, which is describing for us this subject. But in order to quantify how these concepts are going through this distance, through the hyperspheres inside, we need to look at velocity matrix. If we would take two similarity matrices in different moments of time and subtract them, we would have roughly speed, velocity, with which two concepts are approaching each other for this certain time step. Of course, the setup is a bit different, not to make too complicated. It's a general idea behind this. But if you would have a velocity matrix and do the spanning tree algorithm on it, we will see with different picture. We will see those concepts which attract the most attention for this specific time period. And this describes for us the so-called hot topics when active discussion in the literature is somehow benefits particular nodes of a network. So particular nodes are attracting other concepts. And in this case, we can see that, please pay attention, that we have, for example, in each star inside, we have a red dot. This red dot, the colors, represent for us the derivative of the entropy. And roughly, it says us that this concept became more popular over time. The interest is increasing about him, and all others around him is those which are attracted to this particular concept. And our studies show that in most of the cases, the entropies of the dimensions, of the stars, we will call, for example, these leaves, of the star. The entropy of this concept is slightly decreasing, so they kind of give the energy to this central concept, which is in the center of the star. And his entropy is increasing. We want to quantify this. So this picture is tell us how in the network the new knowledge is originated through the active discussion, which is kind of devoted to a particular nodes in the network, which increases the energy of this network, the entropy of this network, and which other parameters can be also introduced to say that this dynamic give us the way to record the new knowledge in the system. We can say that dynamics of these clusters that we have, for example, Wilkinson microanisotropy probe, in this picture, we have a histogram of a vertex order. So how many leaves particular concept has at specific moment of time. For example, Wilkinson microanisotropy probe have something like 32, more leaves, for these dimensions or connected networks in 2004. And this impact is decaying over time. And on the other hand, we have a repulsion. It's compared to the negative frequencies. If attraction, when we have that concepts became polar, repulsion tell us that the concepts go apart, because of such a relaxation process in the network happens, and the active discussion is succeeded, and we have some relaxation. It could go again to contraction, but that's another story that we will discuss later. But in this case, I want to say that these clusters that we have, it's like disruptive changes in the network, that produce new knowledge. It is stored in the network, and we have to understand how we can predict the appearance of these stars on the velocity matrix, because essentially to be able to predict a hot topic, it's something that would lead us how we can predict a knowledge, a novelty in the system that would be introduced later. We can see also a very interesting fact about the size of these clusters, that if you would take, for example, one seed concept like dark matter and build a huge similarity matrix, and then velocity matrices, etc., and build a distribution of a size of the cluster along the years, we would see that it's essentially a linear, well, not linear, it's a power law dependence, with exponent roughly for this concept is 4.03. Yeah, here is formulas how we can obtain the exponent and the error, yeah, for it. And well, the systems which exhibits a power law dependence is really very widely present in the nature. Still, it's remains equations why we have exactly power law dependence. Why the systems start to behave like this? But in this case, we see the same behavior, but we hope that in the future we will be able to explain from this data inference to understand why it has such a power law dependence, what leads to this. Because, yeah, it's a kind of result which is known for other systems, but for concept networks, it was not discovered. We have this here. Let's discuss in more details how we can bring the thermodynamics and explain in terms of thermodynamics the states of nodes of this network. This is very interesting from that point of view that many debates now are going about whether we can say that information entropy is the same as thermodynamic entropy. Can we build a bridge just because of it's the same name? Yeah, it's not very good explanation, and there is a lot of debates about this, but we can say one thing, that entropy itself, there is no the entropy of the system. It's a function of a state, but state is that state that we are measuring. Our ability to measure the information about the state is defined for us as entropy. We can have many entropies for the same very system. It depends on how good we are in measuring the state of the system. And I can illustrate this on this example. For example, we have a number of documents where we know that some particular concept exists. We have certain probability to find this concept among these articles. And this probability would be 1 over number of these documents that we know. And in this case, that would be uniform probability. We only know that in these articles exists a particular concept, and this uniform probability tells us in some sense nothing. So we are in a state of complete ignorance about the system. In particular, we don't know more details about it. And the entropy of this state would be maximal. It's a logarithm of m, which is kind of known result, and it's many times kind of mentioned in the literature, but without a connection to a particular state. But if we would go deeper and we are able to analyze something within articles and understand, for example, how many times this concept is appeared in particular document, we can make certain granularity of a state we can reshape it in such a way that probability of finding a concept which would be decided exactly I times, for example, would be given by P meso probability. And this P meso probability, if you would build the entropy out of it, it's already known thing that we have entropy in this way. It would be P log P, or this is entropy per document, yeah, conditional entropy. And this entropy would be much smaller, well, smaller than S micron, because we have more knowledge about the system, we have no more information about the states, and in this case is entropy, the very same system is decreasing. But another question is, are we able to say something about, in more general case, how we can introduce the macro state in the system? If we would smooth the meso probabilities by saying that let us maximize the entropy of this state, introducing some constraints. This is known Jane's Maxent method. When we introduce some restrictions, yeah, in Lagrangian on first moment and log moment of this distribution, we would have a maximized entropy in the way that is shown here, like S max, yeah. And we say that S max can be represented like entropy which has direct relation to thermodynamic entropy, where average of logarithm TF is energy and TF is the number of particles. So the system can be viewed in two ways. It's or ground canonical when lambda over beta is chemical potential, or it can be treated like canonical system because this average of TF is essentially also an energy. Well, yeah, it's another problem. Sorry, some graphs I didn't recognize, but you see the dynamics of the picture is working. So if we would try to estimate these beta and lambda parameters of the distribution, the macro distribution that we have here, it will tell us we can find these parameters for every concept that we have. So we have a distribution for each concept, and we take these parameters, we can estimate it from data, and we will see that these data show us essentially two phases. And these two phases are corresponds to, well, we can say linear and logarithmic spectrum. Yeah. The most interesting thing here that when we have this beta, you see the big peak, yeah, of the most probable, I would say, the temperature, because beta is essentially inverse temperature, corresponds to the peak of this beta distribution. Yeah. So most probable value for the temperature would be 1.5. Yeah. And this is interesting result that needs to be understood in terms of dynamics of a network, which we will try to do. Yeah. So what we can say, if we say that we have S max as thermodynamic entropy, we can try to introduce other thermodynamic potentials, and via state diagrams understand the limitation of a state space that we have for this particular network. For the entropy, we can say that this phase SE diagram, in theory, on the left, you can see it looks like this. That's left corner, left, right, lower corner of the slide. We can see that entropy can be low if we have all the concepts, yeah, have particular citation once, for example, in all possible documents. And we also have overcritical state when we have, for example, like something like K max, yeah, the maximum possible distribution or maximum possible citations, for example. And all the documents have it. Then entropy would be low, energy would be maximum. In physics, these states represents lasers, for example. Yeah, it's overcritical, which can be described by negative temperatures or, well, excited states. But more conventional, we have situations when we see this concave curve. When on this curve we have a thermodynamical stable states, so states in thermodynamic equilibrium. This is what we have in theory. Yeah. But if we would build the same thing for our system, we would see that some nodes essentially are on a thermodynamic equilibrium curve. Yeah. But many more of them are excited. And this excitation is that what brings some, well, interesting behavior to the system, because excited states is actually non-equilibrium states, and their dynamics is what we need to understand in order to understand how their knowledge is produced in this system. We can observe the dynamics of particular concepts in the system, how they move through this concept space, and we have three concepts here mentioned on the left corner of the slide, and we can see that they are pretty fast. They are moving unpredictably like Brownian motion, yeah, but within some concept space that we have here. And this projection that we have, this shown by arrows, it says how we go from meso state to macro state. This is a projection to thermodynamic stable states from non-stable. And this dynamic is, well, we will try to understand in more details. If you would say from another phase, which I said it's corresponds to linear spectrum, yeah, we can say that this state is a state for new concepts. This because we have, if you would go look deeper in the distributions, we would say that in this case we have very small amount of documents that describe other concepts. So most of the new concepts are introduced here, and then they go to the another phase with this high peak, yeah, which in this transfer kind of show us how the novelty is introducing in the system and how it's adopted by the network in general. The model itself, if you would project all the concepts on a thermodynamic stable curve, we would see that the blue line corresponds to essentially lambda equal to 0 when we eliminate the phase with the new concept, and this corresponds to thermodynamics essentially from physics. When we have these dashed lines, it shows when we increase lambda, when we increase insufficient amount of information in the system, it becomes perturbed. We can go to the red line, and this red line corresponds for us this another phase, yeah, that we show here. Red dots below this red line show us the states which are overcritical in terms of this beta negative that we have here. Yeah, you see, for example, on this slide, we have almost closed curve below, and these red dots that we have here, they describe for us the overcritical state, like lasers, for example. Okay, here is, sorry, it's kind of, well, I still will have a very small amount of time to proceed, but the thermodynamic potentials, specific heat susceptibility can be introduced in this system. Here was the formulas for it, but you can find it in the textbooks also. What we do, we calculate the heat capacity for this network, and we can see that around the temperature, which is exactly like 1.5, yeah, in beta, but in terms of T, it's 0.7, sorry, we have a peak. And this peak, usually, well, in physics, there would be kind of like lambda point, yeah, phase transition that happens in the system when we go through the temperatures. In this case, we can say that in the system, we have a large amount of oscillations of energy and a number of documents around this critical temperature. And this seems to be a critical point where all the system is attracted to. It tries to go in this area all the time, and this remains to be discovered why. In this case, we have a susceptibility, which show us the oscillation in number of documents. And you can see, for example, for C2 concept, which is differential scanning calorimetry, for the 5 years, the 4 years of its dynamics, we have huge oscillations in the in number of in average TF, I would say. Yeah. And we can see that system is divergent around this same temperature. When we say about the entropies, about entropy of meso and macro, so thermodynamic entropy and empirical entropy that we can calculate for a system, the difference between these two quantities can be formulated in terms of residual entropy. And this residual entropy actually is the size, it's amount of information that system, that particular concept keeps. And we can see that for the temperature 0.07, we still have a divergence of this quantity here. So the amount of information is maximum at this point, and system in dynamic tries to go in this region. Well, I will conclude because I think already it's about the time. Yeah. So the studied system and well, this knowledge network indicates a number of potential research directions. And well, we can say that we can study on experimental level the system with power law dependence, power law distributions that well happens everywhere, from earthquakes to people income and etc., etc., etc. If we would study this system, we can find the models that would be beneficial to understand how this happens in different fields. We show that the size of the topic clusters follows essentially a power law distribution, and the explanation of this distribution within this framework will allow us to say something more about other fields. The temperature dependence of the heat capacity and susceptibility that can be calculated for this system indicates the presence of a phase transition, but this phase transition is something which resembles some properties of a phase transition from physics. When we have a temperature, a particular temperature for the phase transition, but it essentially has a dynamic nature. And this phase transition can be formulated differently, and in order to understand the self-criticality of this network. We can say that entropy production is not always positive. That I will show you. But on average, we can say that second law, which corresponds to well, the limit, it's R to 0. In this case, we have entropy of a system, which corresponds to thermodynamic entropy. This entropy production should be always positive for physical systems. But in this case, we have violations of this fact, and understanding how it happens on a microscopical level, it's an interesting discussion. Yeah, we have some results about this, but maybe we'll discuss it a bit later. But we can study how second law is originated, yeah, to prove it within the system. The concept of thermodynamic work that will tell us how these stars that I will show you before originated it still has to be formulated within this developed thermodynamic approach. It requires essentially a not mononode approach, and we have already some results about this, but that would be too big discussion for now. Yeah, we will maybe next time talk about this. But it essentially requires the minimization of beta free energy. It's also possible in this system, and in this way can estimate the free energy, and this free energy will tell us how we can go closer to concept of thermodynamic work in this system. And also, we built some state diagrams that estimate the state space limits for concepts. We know, for example, what range of entropy production exists in terms of energy and entropy for a particular concept, and we know which concept in this case has to be excluded when we talk about the concept thermodynamic work. Well, that's it. Thank you for your attention, and please, if you have questions.
Hello, thanks for the talk. Yes, nice. Uh, quite physical for me. I mean, I get the general idea, but can you maybe lay out a couple of examples in terms of specific grants or projects that you would like? For instance, I could see a very interesting application to take this into maybe my field. We could write a paper, for instance, about the tools, how to use the tools, etc. But we would need like a little bit of something to latch onto, you know? So if you can give like a couple of examples, like specific examples, like this is something you can watch the research field move into this area, then you could see an explosion of research over time, and then you could see maybe it move the other direction. And you could, that would be, in my opinion, a very nice. Do you have some examples like that, maybe, or something like that?
Well, we try to build a model which will explain for us how this explosion is originated. Yeah, and well, in connection to the fields when it can be used, it's in connection to the Wikipedia papers, for example. There is a research which follows nearly the same path, but makes it a bit in a different way. Yeah, with maybe they operate with less amount of data, which can be extracted, of course, from the Wikipedia. But we can estimate, for example, the efficiency, as they did, yeah, efficiency of Wikipedia pages, and maybe to find the pages in Wikipedia that needs to have a more attention, yeah, something of this kind. So it can be reformulated in terms of number of reviews of a particular page in Wikipedia, which also essentially a power law dependence. And the cutoff is tell us, for example, new pages have not that much of the reviews. And in this case, they correspond to a linear spectrum. If some pages has a lot of reviews, they would have, for example, this logarithmic spectrum, yeah, which goes from power law dependence, yeah, of the citations of reviews. And in this case, we will be able to understand, for example, which pages can be introduced, for example, in Wikipedia, yeah, in the future that would benefit some new knowledge that will be originated or explained, for example, in here. But it needs to be explored. Yeah, it's the method, and this method gives you some new parameters to trace the states. Yeah. On a new level. So in physics, we measure in the states in terms of temperature, different thermodynamic potentials, etc. In information science, we usually have information entropy as a tool to measure the state. But in this way, when we map this distribution that we have on, well, that would be kind of Boltzmann distribution, if you say, from physics. We can introduce many more measurable parameters to a particular entity in information science. It could be concept, it can be article, it can be journal, it can be article in Wikipedia, it can be some financial asset or whatever. So we can take this method in order to put many more sensors on a particular information entity and trace its dynamic to see what is happening. Because the next step here would be to build well, the equation of dynamics, yeah, for example, the master equation, yeah, which would tell us, for example, the probability how two concepts or two nodes of information, yeah, can be closer or further. So we want to understand what would be the probability of a next step, having the previous history. And in this case,
Yeah. I think I get that. I get it. What I think we should do, would you like, this is my question perhaps, would you like, I think maybe you and I can, in psychology, I'm a psychologist, we can do the same analysis using your code, all the, you know, etc., for psychological concepts. And we could write a paper perhaps, and we could say, okay, we see that this model predicted open science would be cool in 2015, and we saw that it received millions of funding, et cetera, et cetera. Now in 2025, we predict that these 10 concepts are going to be the next ones. You know what I mean? Like, and then we could say, then we could start writing grants for them. And we could say, you know what I'm saying? Like a few examples like that, I think would take this.
We were discussing some, well, the problem here is only the source of information, yeah? One of the possible source of information, as I was discussing with Camila, is the GStore. We can talk about this, yeah? One thing is Wikipedia data, but another one is GStore, where we can take all the data, but we need a dictionary for some psychological concepts that we can take out of there and do the same analysis to understand how the psychological concepts are developing over time. Yeah. What are trends, for example, it can be made through the topology. Yeah. But to understanding what would be the future steps, the prediction of some future steps, it needs to be done via the thermodynamics. This model is telling you what would be the next step, next state for concept having, well, measuring its entropy. So you measure entropy, you understand what would be the next step in terms of other parameters. That's how it can be, can work.
Should write that paper. If you have the code, maybe I can do it, or we can hire a research student. It can be their master thesis. And perfect.
We will talk about this. Yeah.
Could we go? Right. Okay, could you please go to the slides where you introduce the meta states? Yes, that one. So could you please define TF and beta and maybe lambda?
Yes. I was, yeah, too much introduction. I mean, technical details that need to be explained even more detail. You see, the meta state is something that we going to have back. That's how we work. In meta state, we kind of put concepts that have the same citations in one minute. For example, you collect some citation that appears only once across all the documents, and it would have certain probability. Yeah. Then we can go to arguments, and in this case, build a whole distribution which is exactly this bar. Yeah. We would have many more documents where concept is happening only once. it would correspond to 0 entropy here. That's a good thing. Next, we would have less number of entities which have addition 2 times. Yeah, and etc. But when we will build the entropy, we will use the exact formula to understand how entropy per document. But in this case, we can say that we would have multiple variations of root bars. For example, like it done in the Thermodynamics, you do an ensemble of different probabilities. You put them together, and you say they all slightly different, but you keep certain properties in each of them constant. Usually, we keep something that we want to keep in physics. It's different stuff, yeah. But here is nearly the same. So we have the distributions of the state. We want to keep the average of the first log of the first moment and first moment of the distribution. And if we keep constant in all of them, we can produce millions of them, and that would be well, actually probability of these states in different ensembles, and the average over this. Doing this, we can estimate the most probable state. Yeah, most probable state among all those that we have, keeping these things constant. Doing this, we will get this type of distribution. It's essentially powerful, yeah, with exponential power. Yeah. So powerful with exponential power is something which can tell you the most probable distribution for keeping these things on. It's in line with this James-Marcel method. You have entropy and you maximize entropy. I didn't put Lagrange here, but you can say, okay, you have this, we have constraint that this should be normalized to a unit. Yeah. We have to keep constant this one, and we have to keep to constant this one. Yeah. And well, varying this Lagrangian, going to maximization, yeah, we have the equation that will give you this particular state.
Okay, so
It's a polygon. So this is kind of gravitation function, yeah, this case. And if we take a sum over all possible I, you would get the normalization. You would get a polygon, yeah, of beta, yeah, beta minus. So if you would say that that's now that goes to 0, you would have a delta here, which usually corresponds to canonical ensemble physics. Yeah. And yeah, it's that would be under the first phase thing. But if then we have azimuths, we have entropy in this way, and we can compare this entropy to thermodynamic energy. And essentially, this one goes to the energy, better inverse temperature, and lambda, well, on this place, it's better, we can take it out of brackets, minus lambda over beta, that will be chemical potential, as it usually defined. So in this case, we have a direct correspondence of that what we have here, entropy to thermodynamic energy. We can also recover the Clausius, yeah, pure Clausius relation. I didn't show it here, it was already too much. But we can say that it's interesting, right? The distribution, if you would build, for example, something like entropy efficiency, entropy over the energy, all of this average of there. This entropy efficiency is maximized when we have our law distribution, and it's maximized to the value beta. And if we separately have a linear spectrum, lambda is also maximized to this entropy efficiency. So we can say we have two general, say, like the second law of thermodynamics. You know, the entropy is growing for closed canonical systems. Yeah, it should grow. We see it also here. Many more concepts go to the maximum entropy, and we tend to go there all the time. But entropy efficiency is another argument, it's another law, yeah, that this particular distribution would follow. Yeah. And we can actually show here something about this. Yeah. First slide. Having been one as energy efficiency, we can have something like entropy reduction ratio, or efficiency reduction ratio is called in literature. And it has a structure like this where A is essentially having all its free energy. So these relations are all defined by residual energy. Pure information theoretical quantity in terms of thermodynamic quantities. Yeah, you see here is the thermodynamics, here we have information. And this equation for R is a good thing when you differentiate it. With time, you have an energy production system. And the second law and other things. And if you are to zero, which essentially goes to thermodynamic, we can recover the causal center, which is stable. So it's a direct response of information to thermodynamics.
I have a question, not really it's related.
Okay.
A methodological question that we related to Fred's comment. I wanted to talk about, ask about those concepts. How did you get them from rocket science? Did you generate them yourselves, or did you take those concepts that rocket science generated, and how those concepts are generated? The question is because I was wondering how this method is robust or universal across different databases, or
Yeah.
can you use it for science?
That's a good way.
So I was wondering about the collection of concepts. Where was the cutoff? So it's related to your question, Camila. And also another question, can you predict new concepts using this method?
That's exactly our goal. Yeah, to be able to produce a novelty and to be able to produce new concepts. Yeah. Well, the first thing about the database was taking data from rocket science. Rocket science is already a vectors of science-wise platform, which were analyzing the concepts in the scientific literature, and it's already closed. Now it's processed. So we had a common project in the past, and we have a database from them, and they published a few papers. How they were generating concepts, how they made this disambiguation of different synonyms and so on and so on and so on. So in their case, the vocabulary, the amount of concept is not stable. They always consider something new, and they were introducing to the system and recalculating through the literature, trying to understand when the concept was originated in the literature, yeah, and then put it. So we have exact data when the concepts are introduced in the literature. Now we decide, okay, let's trace this one and we start from this date. No, it was traced before. So in this case, we kind of understand it. It gives us a possibility to understand if we have some critical state in the system that will produce for us a new concept or not. So this situation is that what I'm studying. Yeah, we have roughly 700 concepts. That was very new, and only some of them was transferred from phase 1 to phase 2. And these 7 concepts, I'm studying heavily to understand how they were introduced in the system with kind of what was the state before and what is the state after, and so on. Well, obviously the number of concepts is growing in quantity. We need to introduce something new. That's why if, for example, use a new data source about stability, I would say the words later. If we use a new data source, briefly we can use some distinct words that exist, for example, in literature at all. the difficulty would be to take some of them and put that they mean exactly the same thing. So that was made by science-wise. They were saying that we have a concept, we have a synonym of this, synonym of this. It would be abbreviation and so on and so on. So if any of this happens in the literature, it is regarded to concrete case, the concrete concept. This is kind of thing which was made by them. I didn't do it. I just took the data and I have 500,000 papers and 40,000 concepts. And about the stability, we can say that if we would calculate the entropy, that measure entropy that I was describing, it is simple. Sorry, that's way previously. The dynamic will show us some time series. Yeah, the entropy can decrease and increase because the number of documents are constantly changing. We have open systems. We have this. But if we could start, for example, remove from the data set where we were calculating this entropy, the articles. For example, we arbitrarily remove up to 60% of articles. The profile, the entropy profile, will remain the same. So it's essentially tell us that we have a cumulative effect. So it's not the presence of a particular article which gives you all the picture. It's really a lot of articles which contribute to a particular feature on this entropy profile. So, well, we could trace a new one, that would be obviously some different picture. But in terms of old one and sufficient data here, I think we are fine. Because if you have, for example, many, well, 40% of this number, we will still have the same profile for the entropy, which tells us that the behavior of the system is there in our data, and we can try to take it. So the stability is good, but the number of concepts, of course, can be increased. And in terms of new concepts, the novelty that we were talking before is something which can be, which should be introduced. Sorry.
Do you think, in your experience, are the ones that explode or the ones that get a lot of citations, blah, 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 have a lot of energy, temperature, are they new keywords or are they old keywords that kind of have a new thing added or something like that?
Well, in correspondence, the number of new concepts in comparison to old concepts, of course, is very small. So we have less new concepts, introduced. So most of the cases, all the discussion is made of old concepts. So they change the context, they change the leaves, and they change the way they interact. So I hope, for example, that what I see, new concepts when they originated somewhere near such a star. When they originated, when they are new, they can be connected to some of the nodes, but then they jump to absolutely others. So the new concepts are really very unstable across this network. They introduced, but because they are introduced only in a few documents, their state is very perturbed, I would say, and they easily can connect to many others. So their meaning is not stabilized. They can get a new meaning through the literature and jump all over the places. But
I think if we took like one hot topic across, let's say 4 or maybe 10 maximum, I would say, fields, and you traced it in this graph, like every 5 years for 20 years, let's say, like from 0 to when it's a huge topic, like open science, if you picked open science, like, and just showed it each year or every 5 years, that would be a very high interest, high impact paper in my opinion.
So it's possible, yes, of course.
Yeah, we should do it. I think it sounds easy.
But then we need
I mean,
about this article. this possible. So we will have a whole connection of hot topics that where exists, yeah, along the way in this literature. So I'm now, I have a huge graph of this when we have not only one particular concept which kind of collects all those, yeah, key concepts, but a huge graph of many more others. It would be very bad here because you would see just wow, a lot of lines, a lot of dots, and it's not very representative. But this graph exists, so in principle we can list.
Yeah. Let's do, okay, I'm thinking already maybe two or even three. One paper, like 2 topics that go nowhere and show how they change or they stay the same. 2 topics that are like average and 2 topics that are top, and just show like year 0, here's the picture, year 5, here's the picture, year 10, here's the picture. And you can, you know what I'm saying? And you can just say, okay, like blah, blah, blah. And this is how we created those pictures, let's say. That would be one. So you can compare unsuccessful versus successful topics. And then another paper could be like, here are 10 successful topics and how they traced their, you know what I mean? Maybe I think those would be 2 very interesting, and it sounds to me like perhaps you could do it relatively easily. I'm not sure, but
you just need to take this data from GStore. I think we're already on the right way to refresh this from high level physics to other disciplines, and yeah, it's possible. The general theory of prediction, how these links are predicted, and whether there will be another link or there will be another star, it still remains to be kind of calculated, because the maximum equation for this is huge. It's a very big one, and it's well, so far it's need to be a little bit of cleaning what states we have to omit, because for example, I can say that the center of the star, the concepts in thermodynamic equilibrium is very rarely appeared in the center of the star. They already have so huge entropy that they cannot go further. They can increase their temperature, but to be a center of discussion, no. So the center of discussions, this is a particular part of the concepts which don't have a very low entropy, don't have a very high entropy. So it's well, these collections is what we need to look for to understand whether we will have a new hot topic somewhere.
Yeah.
Thank you.
Any questions from you?
Yeah. Okay, so we will be closing. Brett, you're welcome. Come here. We will go.
Yeah, thanks for the talk, man. I don't know. I can't really hear you that well when the microphone is not pointed right at you. Yeah, sorry.
I don't know where the microphone is here.
But but I would be very interested in writing one of those papers and helping you write it if you want. Yeah.
Yes, of course, of course.
It's a matter for me. It's a matter of time to learn the process and learn the syntax, et cetera, et cetera. But if you could do it, like if you could produce those graphs and then I could interpret them, let's say, or say, I have also some keywords, databases of keywords, if you're interested in them, but we could talk about it later. Yeah.
Yes.
But I think that would be and it would make the work more concrete, more graspable, because right now it's like a lot of energy, in my opinion, at least as a non-physicist, as a psychologist, energy, entropy,
Like
these are,
you see, when you marry 2 disciplines, when you have a physics and you try to physical methods here, so you need to use those concepts from there. So in terms of that, what we are talking about, the energy in physics has particular meaning. Well, it's different from different branches, but when we talk about energy in terms of information science, you need to have a way to introduce it. It's not enough to say information, it's energy, and there's the information, and well, 1 hour principle. Yeah, everything isn't up there. But you can quantify with this approach how you can introduce energy, what is energy, and use all the equations from physics to work with this system.
yes, I think that's another paper to write, but yeah, because right now, as I said, it's just for me a little bit abstract, blah blah blah. But if you had a couple
my
of,
draft.
Yeah. I'll read it. Thank you again. Huh?
Thank you. Thank you. Thank you.